All right, welcome everyone. My name is Xuan Xiao from AnyScale open source team. Today I will introduce Retrain, a production-ready library for distributed deep learning. And in this talk, I will go over the following three sections. First, we'll discuss the trends and challenges of distributed deep learning. And then I'll discuss how Retrain simplifies the distributed training. And then finally, we'll give a demo about how to fine-tune a Llama 2 7B model with FFDP and Retrain. So during the past few years, we've seen that the model size is getting larger and larger. Like for example, in this diagram, we can see that NLP foundational model size are increasing exponentially fast. So these models are too large to fit into a single devices. Therefore, we come to the model parallelism to shard the model across multiple devices. At the same time, we're building larger data sets to fit these large language models to avoid underfitting. However, training on these large-scale data sets can be time-consuming and computationally intensive. Therefore, we come to data parallelism to improve the training throughput and speed. So altogether, using model parallelism and data parallelism in distributed training can even accelerate our whole training progress and then enable us to train these large models on large data sets. However, there are still many challenges in distributed training. For example, the compatibility issue. The ML developers might working on different frameworks like PyTorch, Lightning, Hugging Face, or different persistent storage. Their compute resource might hosted by different cloud providers or different cluster orchestrators. It's often a burden for the ML developers to build the integrations with all these frameworks and compute platforms. Scalability is not a big issue. Like everything works super well with these deep learning frameworks in a single node setting. But when you scale out to dozens or hundreds or thousands of GPUs, the things get completely different. So how to effectively manage a cluster of computational resource and how to efficiently launch your job in a robust, reliable, and fault-tolerant way. There's no simple solution for now. And for large model training, we cannot solely use data parallelism, but also need to use model parallelism to train these models with limited GPU and CPU resources. So all these challenges I mentioned above seems to be hindering us from going distributed. But today, I'm thrilled to announce that Retrain provides an open source production-ready solution to make distributed training easy. So what is Retrain? Retrain is a library for developing, orchestrating, and scaling distributed deep learning applications. It is built on top of Ray and integrated seamlessly with these deep learning frameworks. And why should you use Retrain? Here are three main reasons. First is a broad compatibility and high scalability, also the great large model training support. When we talk about compatibility, Retrain can be run with any training framework, on any cloud storage, with any compute platform. Let's take a closer look first into the integrations with the deep learning frameworks. So here we show the code snippet. To use Retrain, users need to define first a training function, which contains your PyTorch or Lightning or Hugging Face training code here. And then define a scaling config to specify the number of workers and the resources per workers. And the Torch trainer will combine these two together and help you to launch distributed workers and run the training function on the corresponding devices. So here, we gave the simple code snippet to help you understand how to migrate your code from the PyTorch or Lightning to Retrain. On the left-hand side, there's a normal DDP training script. You have to set up a distributed environment, wrap the model with DDP, set up the distributed sampler to shard your data set. And also, during training, you have to move the batches to GPU. But Retrain provides two utility functions that can significantly simplify your training loop. Just call prepare model and prepare data loader in this training function. And PyTorch Torch Trainer will help you to set up all this distributed environment and corrected devices. And for PyTorch Lightning, we have even simpler APIs. Basically, you just replace the DDB strategy and Lightning environment with our ray trains utility, and just call prepare trainer before you kick off your training. You don't need to change any Lightning modules definition or custom data loader definition. Everything is purely Pythonic and in a Lightning's way. And Hugging Face Transformers, similarly, we have a prepare trainer API that helps you to set up integration with ray train. So as we can see, all these minimum APIs provides a very shallow learning curve for the users to onboard their model training workload from the deep learning frameworks to ray train. And apart from the training, you may also care about how to persist your checkpoint and training artifacts. You may use different persistent storage, like AWS S3, GCS, or many shared file systems like HDFS, EFS, or GCP file store. And Retrain provides a simple interface called storage path here. And the users just need to provide a URI on your persistent storage. And then Retrain will help you to think or copy your checkpoint and artifact from local storage to persistent storage. You don't need to worry about how to handle the file transfer under the hood. Also, people might worry about, like, if my node is provisioned by different cloud providers or managed by different orchestration tools, do I have to change my training code to adapt to these different compute platforms? The answer is no for Retrain. So the ML developers just focusing on interaction with Retrain API. And Ray, with this great compatibility, will help you to set up the computational environment for you. So we also provide out-of-the-box observability tools called Ray Dashboard. Like from here, you can see how many nodes you have in your Ray cluster and what's the memory, CPU, GPU utilizations. Also, you can easily track your training progress with the dashboard, like how many workers you have for this torch trainer, and see the logs or stack trace for better debuggability. You can also check out this metrics dashboard to give you more fine-grained understanding about the hardware utilizations. Like all these observability tools gives you the confidence that you can safely migrate your workload to Retrain and have full control along the life cycle of your training. So apart from the broad compatibility, Retrain is also featured for its high scalability. It's simple to scale out your model training and data preprocessing with a few lines of code change. So Retrain is built on top of Ray, and we have done a lot of experiments to test out what's the scalability of Ray, how Ray can scale to a large amount of GPU or CPU nodes. As we show here, we've successfully trained large language models on 1,000 GPU scale, and also breaks the world records to process a huge data sets. And we also have another session tomorrow to have a deep dive onto Ray scalability and see how to scale the Ray clusters to 4,000 nodes. So as a Retrain user, so we provide a minimal API for you to leverage this high scalability. It's called scaling config. At right-hand side, I gave 3 examples. The first example is scaling out your training with 4 workers, each with 1 GPU. And the second example shows if you don't want a GPU, we can also help you schedule like a large amount of CPU nodes. The last example shows you can launch the workers with customized resources. Here we launched 16 workers each with 1 A100 GPUs. So this easy-to-use API helps you to scale out your training with 1 line of code, and also is flexible enough to support different like heterogeneous types of compute resources. In addition to model training, you may also care about how to scale out your data preprocessing. Like traditionally, if you're training a model with GPU nodes, the GPU nodes also take the responsibility of data preprocessing, which could be a huge bottleneck if your data set is super large or your data transformation takes a long time. So with the strong integration with rate data, we enables you to leverage the heterogeneous resources to collectively preprocess the data sets for training. So on the right-hand side, we did some benchmark. We can see using the heterogeneous cluster with rate data, nearly double the throughput of data ingestion compared with the native Torch data loader. Also, rate data supports streaming execution and overlapped training and preprocessing. All those exciting features, you can find more about this in our rate documentation. And lastly, I'll talk about our large model training support. And as we discussed before, like training these large models, you cannot only use data parallelism. You need also to adopt this advanced model parallelism or zero, this distributed strategies. And currently there are two popular libraries like DeepSpeed and Accelerate that have well support for these strategies. And you can run these two libraries with zero code change on retrain. And we also have two other sessions to give deep dive on how to use these two libraries to fine-tune large language models with retrain. So apart from model training, like checkpointing is another big issue for LLM support. Like for example, the Llama 270B model, if you're saving it in FP16, it might take 140 gigabytes disk storage. Traditionally, we're using an aggregation-based checkpointing where the rank 0 worker will collect all the checkpoint shards from the other ranks and then combine them and upload them to cost storage, which could be a huge bottleneck. Well, all the workers are waiting for this checkpoint to be synced and the GPUs are idling. And retrain provides a distributed checkpointing feature that allows you to upload the checkpoint shard directly from this rank, from all the workers to the cost storage. So we can see here, the CPU memory usage and network traffic has decreased by number of workers' time. So also, this large language model training could be some long-running job. And it could be expensive if you're using these very costly GPU instances. You might want to use spot instance to reduce the training cost. Like for example, on the left-hand side, we shows that the spot instance price are generally 60 to 70% cheaper than the on-demand instances. So retrain provide the fault-tolerant training to support you to train on the spot instances. So for example, one of the GPU node get preempted. And retrain can automatically schedule your node, schedule your training job onto another GPU node and relaunch the training with the latest persistent checkpoint. With the fault tolerance training support, you can have a seamless, robust, and reliable LLM training experience on spot instance. So in conclusion, retrain provides broad compatibility, high scalability, and great large language model support, which makes it an open source, production-ready solution. And today, I'm thrilled to announce that retrain is now generally available. And this is not only a big milestone for us, but also for the whole community that makes the distributed training more accessible and efficient. Yeah. Okay, so also retrain usage is growing really fast. Compared with last year, September 22, we have 15 times more usage, more weekly usage. And also, we are very happy to see that retrain helps the Instacart and also other open source users to improve their training speed and cost efficiency. Like in Instacart, their training workload runs 12 times faster, 8 times cheaper, and training on 100 times more data set. And we also have many other users that bring their success stories to Resummit this year. And I can't wait to see how retrain deployed in production to help them to success. Okay, so finally, I will give a short demo about how to fine-tune a Llama 2 7B model with FSDP and retrain. Okay, in this demo, we first provide a simplified training function that can work on a single device, but with a huge amount of GPU memory. First, we initialize the model from pre-trained weights, initialize data loaders, define the optimizer, scheduler, and gradient scaler, and we start training. Here, we will not show the details of the training loop, but we provide a utility function that trains the model for one epoch and returns the evaluation metrics. And then we call this training function in the main block. So we notice that we are loading the model, the full model, directly to GPU, which means it will take a large of GPU memory to train this Llama 2 model. So you can definitely train it on A100 or H100, but it's due to the GPU shortage, it's really hard to get these instances from the cloud providers. Therefore, in this demo, I will show how to use FSDP and retrain to help you scale out the model training onto 16 T4 GPUs, which is cheaper and easier to get. Okay, so now, before we get started, let's first import several utility functions for PyTorch integration. As discussed before, we import prepare data loader and prepare model. Now, instead of loading the whole model to GPU, we're using prepare model to wrap it around the FSDP and provide the corresponding configurations for FSDP strategy. So we provide the configurations for FSDP, including how you shard the model across different GPUs, whether to use CPU offload or whether to use mixed precision training. After we process the model, now we are preparing the data loaders. Here, we will inject distributed samplers to both the training data loader and evaluation data loader so that it will shard the data sets across 16 GPU workers. And we don't have to change the training loop. At the end of the training epoch, we may want to save our checkpoint. Should we save the full model checkpoint? Actually, it could be very memory and disk inefficient. And it will introduce the extra communication between the rank 0 worker and other worker. Therefore, we choose to use sharded model checkpoint, which means each FSDP worker will save only a portion of the model weights to its local storage. And later, we'll use retrain's distributed checkpointing feature to upload these checkpoint shards directly to the unified storage path so that you can retrieve these checkpoints later for inference or resume training. The interface here is simple. It's called ray.train.report. Just combine the metrics and your checkpoint directory to this API, and retrain will help you to sync up your checkpoints. And now, let's define a torch trainer to help you scale out this training function to 16 GPUs. We first import torch trainer and also two utilities called scaling config and run config. So scaling config is used for defining the number of workers and the resource per workers. Here we turn on the use GPU flag, which will assign one GPU for each worker. So the run config will define the experiment name and a storage path. Here we name it Llama 2 fine-tune demo, and then provide the S3 bucket as the storage path. And you can expect to have your checkpoint and training artifacts under this S3 bucket after the training finished. All right, and lastly, let's combine everything together into a torch trainer, which includes the training function, the input parameters of this training function, scaling config, and also the run config. Note that everything happening here are 100% Pythonic. You don't have to have some YAML configuration files or some complex environment setup. And we can trigger this training workload by calling python train.py on your head node, just like you're developing in a local environment. And retrain will help you to scale out this training. Okay, as the training kicking off, because it takes time to download the model weights and pre-train weights and load it to GPU, let's take a step forward and see what will happen after the training gets started. Okay, during training, we can see we have trained several batches. And from read dashboard, we see all the GPUs, like 16 GPUs, are being used with high utilization. And then let's check out the progress. You can see we have 16 retrain workers, and each are in progress. And for metrics, you can also get many useful information about the hardware utilization, node network, disk I/O, to help you better debug the bottleneck or the issue in your training code. And after the training finished, let's take a look at the checkpoints and artifacts. From AWS S3 bucket, we can see we already persisted these 3 checkpoints from each epoch, together with the parameters, training progress, and training results. And from each checkpoint folder, there are 16 checkpoint shards uploaded from different workers. So you can use these checkpoint shards later after the training finish for offline or online inference or resume training. Okay, so finally, again, retrain is generally available now in RAID 2.7. We just released 2.7 yesterday, so feel free to try it out. And if you have any questions, please refer to the retrain documentation or join our community. And feel free to post any issues or feature requests. And we're really happy to work with you guys together to make distributed training more accessible and more efficient. And that's all I have for today. Thank you all. I'll leave the last couple of minutes for QA.
And thanks for this great talk. So 2 quick questions. First of all, did you guys compare the performance of distributed training on T4 versus like training on one A100?
That depends on many different aspects. Firstly, how many T4 instances you're using for distributed training? Right. What's the global batch size? And what's your what's your sequence length? And it's actually, it's not an easy to answer question because this training speed are dependent on different aspects. So you can expect if you have one A100 and compare with a bunch of T4 instances and training with the same global batch size, training on A100 will be faster. But if you have more T4 instances, as your global batch size grows, and your training speed will be faster than A100 instances.
But it didn't hurt performance, right? I know that it's gonna take longer on T4, but the performance, the final performance, did it hurt?
The performance will not change.
Oh, okay,
because you are using the same data sets and same like random seeds or training progress.
Okay.
Yeah.
And then my second question is for large models, is it only for LLMs or we can try customized foundation models as well?
Oh, retrain is a very general platform. You can train any large models, including vision, recommendation, graph network, every kind of large models. Yeah, thanks.
Hi. So one of the major requirements is to import PyTorch from the retrain, right? And then like change the lines in the code to use retrain. Is there any other way where you don't have to import the PyTorch, you import PyTorch natively, but then somehow wrap the model separately? Like,
actually, you don't import PyTorch from Retrain. You just import from PyTorch. And Retrain provides the integration tools or some utility functions to add on, add on top of your PyTorch training code. So there will be no like discrepancies between your original training code and retraining. Yeah.
Hey, I saw you have some like a demo and example on data parallel. I'm wondering for the pipeline parallel, does the user need to specify the layer config or pipeline parallel config, where the framework can do like an automatic shard model directly?
Oh, so if you're using pipeline parallelism, other model parallelism, you have to configure the parallelism strategies by yourself. So Retrain provides a unified interface to launch this training worker, and the users has full flexibility to configure how to shard your model and how to schedule the model parameters on different devices.
I see. And follow-up question is there any plan to integrate with something like Alpha to make the pipeline parallel automatic?
I think like integrating with this more advanced training strategy is always our like future plan, and we also want to optimize the training speed by like analyzing the like network topology and analyzing the model size and your training strategy to generate an optimized solution to accelerate the training. So that's definitely on our roadmap.
Thank you.
Could you actually elaborate on that last point? So like, what are kind of the bottlenecks when you look at Retrain in terms of training speed, at least in the current iteration?
Which one?
Or just like, what are the major bottlenecks that are preventing Retrain from being even faster?
Prevent from Retrain become faster. I think because Retrain is built on top of the Recore, the scalability part is guaranteed by Recore. And the bottleneck could be the underlying communication, because currently PyTorch or DeepSpeed are leveraging their own communication libraries. So that's so we are dependent on this open source libraries to provide the efficient training experience. So it could be a problem that they have some bottleneck issue that is not resolved by, like that is not handled by Retrain side. So yeah.
So follow up on that question.
Okay.
I know Recore, you said the Retrain is built on top of Recore.
Yes.
When it comes to when the trainers are running, most of the operations are done by the framework, plus the communication, like the nickel from NVIDIA. So when the trainers are, like the job is already kicked off, what is the role of Ray in that process?
Yeah, that's a good question. Like Ray firstly take care of the resource management and how to launch a job. And also it helps you to orchestrate on this different computation resource, like how to support the fault tolerant training and how to like coordinate between each workers to upload the checkpoints, and how to integrate. Actually, we have integration with read data and retune that can provide better performance on data ingestion and hyperparameter tuning.
Okay.
Yeah.
That was a follow-up. So my original question was with data ingestion, and you mentioned heterogeneous cloud, so
Yes.
that pre-processing can be done on maybe the CPU parts of the cluster.
Yes.
Is there a chance to integrate with a lot of image processing? It's intensive, and you're able to use, say, DALI from NVIDIA to do the pre-processing on the GPUs, where the next step, like in the GPU CUDA stream, you're able to overlap, like utilizing DALL-E. Does Ray provide that, or is it on a roadmap?
All right, that's a good idea. Like currently, we only provides the, I think currently Ray Data has the unified interface called map batches that can put any preprocessing or transformation function into that. So as you said, if you want to fine tune, or if you want to transform image datasets on GPU, that's totally possible with current Ray Data support. So the users have the flexibility to define the transformation function.
Okay, thank you.
Yeah, thanks.
Cool. I think we're at time, but we could fit in one last question. Was there one back here?
What integrations are available with model repositories for persisting weights? I know that in this example that you gave us with the LLM, it's not quite as relevant, but for other models where you would be iterating.
You mean what persistent storage?
Model repositories so that you can persist the weights as artifacts and reload them for additional fine tuning.
Oh, actually, for now we are leveraging the. Let me find the slides. Yeah, we're leveraging the Apache Arrow under the hood to sync your checkpoint to like this cloud storage. It includes, like basically on this slide is most major cloud storage we have used for retrain. So there are also some community contributed integration with this cloud storage, which I didn't list it here. But I think retrain provides a flexible interface for you to integrate with this new model registration, like MLflow or some other experiment tracking tools. I'm not sure if it answered the question.